Hello, and welcome back to Oceanography 106 Lab. I hope you enjoyed last week's exercise, wrapping up our Chemical Oceanography unit. Today, we will begin our Physical Oceanography unit with a lesson on waves. First, what are waves? Waves are defined as the rising and falling of ocean water due to a disturbing force. Most often, the disturbing force is the wind. This is different than tides because tides are primarily caused by gravitational forces that are exerted by the moon and sun. A wave can be generated that is associated with tides, but we will not be focusing on those waves in this exercise. As the disturbing force interacts with water, energy is what's transferred. It can be transferred laterally and vertically, so it's important to note as we go through this presentation that waves are the transfer of energy, not water. The water is just a medium through which the energy travels. The crest is the highest point of the wave, like a mountain peak, while the trough is the lowest point of the wave, or valley shape of the wave. The wave height is the vertical distance between the crest and the trough. The wavelength is the horizontal distance between two consecutive crests or two consecutive troughs. Either can be used to determine wavelength, but you will not determine wavelength from measuring from one crest to one trough, or vice versa. This dotted line is the still water level. It is the level at which water rests when there is no movement and no disturbing force being applied. This can be in the ocean or in the tanks that you will see in the lab portion. Water depth is the vertical distance between the still water level and the ocean floor or bottom of the tank. The amplitude is equal to half the wave height. All of these parts of the wave will be important for you to remember as we continue with this lab. Wave period is the length of time that's required for one wavelength to pass a fixed point. For instance, if we have this diagram, we may choose any point on our diagram. The wave period is the time that it takes for two consecutive crests to pass that fixed point. A longer period indicates slower travel of waves. Another, more accurate term for wave speed is celerity, which defines how fast the wave moves. When we measure the celerity of the wave, what we are really measuring is how fast the energy is being transferred. Celerity is associated with the speed of energy as the water is not progressing, and therefore no mass is moving. The equation for this wavelength is wavelength over wave period, which creates the units centimeters per second. Remember back to the formula we have used before, distance, or wavelength, divided by time, or wave period. This slide demonstrates the difference between a high energy and low energy wave. The low energy waves have a much longer wavelength than a high energy wave, a smaller wave height, and will also have a longer wave period. With a high energy wave, we have a short wavelength and a short wave period, greater celerity, and a higher wave height. Now we will be reviewing progressive waves. They are called this because the waveform progresses through the water away from the point of origin. They demonstrate a lateral transfer of energy, in which energy is transferred in the direction of the wave. If you are standing on a beach and see a wave moving towards you, the wave was created at some point and is transferring energy from that point towards you. Particles and objects in the water will exhibit a specific circular pattern known as orbital motion. This occurs when energy is transferred through the water vertically. See the boat pictured here as an example. The boat moves in a circular motion on top of the wave. The energy moves through the toy boat until it completes one full orbit on top of the wave. Notice that the particles do not progress. Again, it is just the energy of the wave that is moving forward. Standing waves are the final type of wave we will discuss today. Standing waves are not progressive in that they do not move laterally from one point to another. These waves move vertically up and down because water will oscillate between fixed points called nodes without progression. Crests become troughs, and troughs become crests. Primarily, this is due to the reflection of energy off of a barrier such as a seawall. This most often occurs in areas of man-made structures where waves cannot normally break and release their energy. In the lab today, you will see the generation of standing waves in tanks. The smooth, solid glass surface of the tank does not allow any energy to dissipate, but instead reflects until a standing wave is generated. This diagram demonstrates a standing wave. A node is the point at which a wave pivots. There is no movement. Nodes are located at the standing waterline. The antinode is a point at which the wave oscillates vertically. These are the points where the troughs become crests and vice versa. The D to L ratio will determine how the wave should be classified. It is literally the ratio of water depth to wavelength and can tell us if the bottom of the waveform interacts with the seafloor. Waves can be classified as deep water, intermediate, or shallow water waves. The tanks we will be using in this lab are not this large enough to effectively demonstrate the wavelength. So for this class, make sure you always double tank length when making calculations. We will review this again in the lab videos. We use the D to L ratio to classify these waves. Shallow water waves have a D to L ratio less than or equal to 0.05. Intermediate waves fall between 0.05 and 0.5, while deep water waves have a D to L ratio greater than or equal to 0.5. In case you are not completely comfortable with decimals, think about these ratios in terms of money. Is 5 cents less than or greater than 8 cents, or 50 cents? A large D to L ratio indicates that the wave base is not interacting with the bottom of the tank or sediments in the ocean. Smaller D to L ratio waves will interact with the bottom of the tank or ocean sediments. The smaller the D to L ratio, the greater the interaction of the seafloor with the wave base. This changes the shapes of the orbits and slows down the bottom of the wave while allowing the top to progress more quickly, resulting in a wave that increases in wave height until it becomes so unstable that the wave breaks. This means that the crest falls over and energy being transferred is released. This will come up again in the lab portion. The approximate maximum ratio for interaction is 0.5. Today's lab will again come to you in multiple parts. Please make sure you watch all lab videos in order and pay attention to the specific types of waves in each. As always, reach out if you have any questions, and good luck.